Welcome students. So last week we have covered chapter 1 and the initial part of chapter 2. And this is the last slide of last week's lecture. So we have discussed this and the answer is C. Okay, for this question, a husband is cooking beef stew for his family in a pan. That is, the answer is C. Okay, C. Covered with heavy lid. The reason is because it has the highest pressure compared to the other options. So when you have higher pressure, your temperature is also high, and with high temperature, your beef could eventually it's easier to cook the beef when you have higher pressure. So the shortest cooking time is C. If you cook the stew with a covered heavy lid. Another example, an easier one that you could relate is whenever you use a pressure cooker to cook your beef, okay, instead of you just boil it under normal stove, okay. So you will see that if you use pressure cooker, your cooking time will be shorter. Alright, so let's proceed with the lecture. So here we go back to the you've seen this term in chapter 1, latent heat. So what is latent heat? Is one example of the internal energy which related with the microscopic energy. Or internal energy. Energy is also known as U. It is the amount of energy absorbed or released during a phase change process. So it can be for solid liquid cases, which is latent heat of fission, or liquid gas phases, which is known as latent heat of vaporization. So now let's look at latent heat of fission. The amount of energy absorbed during melting or freezing, okay, which is equivalent to the amount of energy released during freezing. So latent heat of fission is related with solid and liquid phases. While for latent heat of vaporization, as the name said, it is the amount of energy absorbed during vaporization process, or is also equivalent to the energy released during condensation process, and that's related with liquid and gas. Okay, so now the magnitude of latent heat, the value depend on the temperature or pressure at which the phase change occur. Temperature and pressure at which phase change occurs. So at 1 atm of pressure, the latent heat of fission of water is 3.7 kilojoule per kg, and the latent heat of vaporization is 226.5. Okay, so now let's check this value in your steam table and what are the other names for latent heat of vaporization. So you go back to your textbook, appendix 1. So just now they tell you the pressure, so it's table A5. Okay, so go to table A5. So when you have a pressure at 1 atm or 101.325, okay, just now it says latent heat of vaporization. See, this value looks familiar, right? So this value here, 2256.5 HFG. Okay, so your latent heat, see, these values are the same, 2256.5 kilojoule per kg. Latent heat of vaporization is known as enthalpy HFG. F is fluid, G is gas. Okay, so it's vaporization, HFG. You go back to the table. Okay, HFG. HF is saturated liquid and Hg is the vapor. So HFG is the value in between these two. Okay, 2256. So another way, if it's not given in this table, another way to find the value is by subtracting the value of 2Hg minus HF. So let's try. Okay, take out your calculator and press 2675.6 minus 519.06. Okay, so you will get 2256.5. So I repeat, HFG is equal to Hg minus HF. Okay, and we could also see the effect of height to your pressure and temperature. So atmospheric pressure and boiling temperature of water decrease with increase of elevation. So this means that when we deal with you can see the difference when you want to boil water at sea level and you compare it if you want to boil water at top of the mountain. Okay, so here let's say, okay, in this slide I have the height of Mount Everest. You can just Google this and you see the elevation is 8848 meter, and while in Mount Kinabalu the elevation is about 4095 meter. Okay, so just now is 8 something, right? So your value it could be somewhere in between here. You need to do interpolation to find the boiling point at top of Mount Everest. And for Mount Kinabalu, the value is in between here. So it should be somewhere here. Okay, what it tells you is that at higher altitude, okay, at higher elevation, the atmospheric pressure will drop. Okay, thus the boiling temperature will also decrease. And at sea level we say at 1 atmospheric pressure. So when zero elevation, this is sea level. The boiling point of water is 100 degrees Celsius. Okay, and if you see here from this table 3.2 at 2000 meter high, your boiling point dropped to 93.3. Okay, 93.3 degrees Celsius. So it takes a shorter time to boil water at high altitudes compared to what it does at sea level. Okay, let's proceed to 2.4, property diagram of phase change processes. We have 3 types of property diagram: TV diagram, PV diagram, and PT diagram. T is temperature, V, small v is specific volume, and P is pressure. Alright, so first let's look at this figure. This figure shows the TV diagram for a constant pressure phase change process of water at various temperature. So as you can see here, okay, let's say we have a piston cylinder device that is filled with water, and if we add, okay, you have a piston cylinder. Okay, this is your piston cylinder filled with water, and if you add weight on top of this, okay, this is a weight, right? You add some weight on top of the piston cylinder, your pressure will increase. Okay, this will result in increase of saturated temperature. Okay, so when P increase, your T set will also increase. Tsat is equivalent to boiling pressure. Boiling temperature of water and the specific volume of the saturated liquid. Okay, your V for liquid should increase, but your Vg vapor volume will decrease. So that's why you see here, as P increase, your Tsat will increase. This is Tsat. Tsat is at this point. Okay, the saturated first temperature. Okay, and your Vf will increase and your Vg will decrease. That's why it goes to the left side. Okay, so consequently, this horizontal line, or we also call it saturation line, will become that connects the saturated liquid and saturated vapor. All this point are saturated vapor. Okay, the saturation line connects saturated liquid and saturated vapor will become shorter as P increase. Okay, as P increase, your saturation line will become shorter. Alright. Okay, so as P even increase higher further, the saturation line continues to shrink. Okay, see this point, the one that I circled here. Okay, and become a point when P is equal to 22.06 megapascal. So this point, okay, when you no longer have that saturation line, we call it a critical point. Okay, looks like the definition here. Critical point is the point at which the saturated liquid and saturated vapor are identical. Okay, so where can you get this value? So you need to you can get the value from table A1, okay, for the critical point of TCR, critical temperature, critical pressure, and critical specific volume. So let's look at table A1. So go to appendix A1. Okay, so for example, the figure that we looked just now was water. So here, this is the value. Okay. Sorry. To go back. Okay. Sorry, I have highlighted the wrong value. But here, the second column from your right side, pressure is 22.06 MPa. I just want to show where you can get the critical point properties for temperature, pressure, and volume for these substances. Okay, you can get it from table A1. Okay, now let's look back at our slide. Okay, so I'll stop here and we'll continue in another video.